Hello everyone, this is Jesse Crawford with New York Medical College, and this is the supplemental lecture for two-sample inference. The purpose of this topic is to discuss how we can conduct hypothesis tests and construct confidence intervals that involve comparing two different population means or two different population proportions. The main thing to keep straight in this chapter is the different types of scenarios that you can be in. For one thing, you can either be comparing population means, in which case you're going to use one set of procedures, or you can be comparing population proportions, in which you're going to use a different set of procedures. Also, if you're comparing population means, you need to know whether you're dealing with two independent samples or two paired samples, and you also need to know in the independent samples case whether your population variances are equal or not. Alright, let's go ahead and get started with an example. In this problem, we're interested in comparing the cholesterol levels of active and sedentary men. More specifically, we're looking at high-density lipoprotein cholesterol, which is actually the good kind of cholesterol. So we just want to try to figure out, do active men have better cholesterol levels than sedentary men? In order to do that, we're going to take two samples. We'll take a sample of active men. Here our sample size is 14 and our sample mean is 47.1 milligrams per deciliter, and our standard deviation is equal to 12.3. For our sample of sedentary men, we have a sample size of 9, we have a sample mean of 34.2, and a standard deviation of 12.8. It says test the following at the alpha equals 0.05 significance level, mu1 equals mu2 versus mu1 not equal to mu2. So in this problem, the null hypothesis is saying there's no difference between active and sedentary men with regards to high-density cholesterol. They're the same. The alternative hypothesis is saying there's a difference between them. So this is a hypothesis test that involves comparing two population means, and it involves two samples. So we're going to use a two-sample t-test for means. Now when you're doing a two-sample t-test, it's important that you take into account which assumptions are valid in the situation that you're in. The first thing you need to think about is, are you dealing with two statistically independent samples or two paired samples? Now here there's no type of pairing involved at all. We just have a sample of active men and a completely statistically independent sample of sedentary men. So there's no pairing here. Therefore we're dealing with two statistically independent samples, so that assumption is valid. And once you're dealing with two independent samples, you need to think about whether your variances are equal or different. Now, for you guys, your homework problems are going to tell you specifically whether you're dealing with equal variances or different variances. But in practice, you can actually conduct a statistical test to make that determination. Just eyeballing it in this problem, you see that we have a sample standard deviation of 12.3 and a sample standard deviation of 12.8. So it seems pretty safe to assume that our population standard deviations are equal in this case. Finally, in order for this t-test to work, our populations need to be normally distributed. So that's another assumption that's required in order to do this type of problem. We're going to conduct this hypothesis test in much the same manner that we conducted the hypothesis test in previous chapters. It's a two-step process. We're going to start off by calculating a test statistic, and then we're going to compare that test statistic to a cutoff value to see if we reject the null hypothesis or retain the null hypothesis. So let's start off by calculating our test statistic. You see that we have this formula for our test statistic t, and it involves x1 bar and x2 bar. It involves n1 and n2, and all of those numbers are given to us in the problem. But you'll also see that it has the letter s here. And you might be wondering, is that S1 or is that S2? Well, it's actually neither of those. It's a pooled standard deviation estimator. So remember, we're assuming here that our population standard deviations are equal, and what S represents is an estimate for that overall population standard deviation. So let's go ahead and see how we calculate that. This is the formula that we use to calculate S squared. You can see this formula is kind of ugly, but it's not really that hard to deal with. It just involves n1, n2, s1 squared, and s2 squared, and we have all those numbers in the problem. So we can just plug those numbers in, and we get s squared is equal to 156.07. Of course, in order to find s, we need to take the square root of that, and we get 12.49. Now we're ready to finish calculating our t-statistic. We just take all the numbers in the problem and plug them in, and we take the value for s that we just computed of 12.49 and we plug that in, and we get a value of t of 2.42. So we're done with the first part of the hypothesis testing procedure, which is to calculate our test statistic t, and now we're ready to try to compare that to a cutoff value. So the question is, what kind of cutoff value are we going to use? Well, because our sample sizes are so small, we need to use a t-distribution cutoff value. And a t-distribution requires you to know two things. You have to know your confidence level, or your equivalently your significance level, and you need to know how many degrees of freedom you're dealing with. When you're doing a two-sample t-test where the samples are independent and the variances are equal, the degrees of freedom is n1 plus n2 minus 2. So we just take those numbers and plug those in and we get a degrees of freedom equal to 21. Then we just look at our alpha value, which is 0.05, and we see that the cutoff value we're going to use on this problem is 2.08. Since our cutoff value is 2.08 and our t-statistic value of 2.42 is in the rejection region, we're going to reject the null hypothesis here. In other words, we're rejecting the hypothesis that mu1 is equal to mu2. And in the context of this problem, that means we're rejecting the hypothesis that active and sedentary men have the same values of good cholesterol on average. Furthermore, we see that the active men have a sample mean which is higher than the sedentary men. So this study actually provides pretty good evidence that active men have higher levels of good cholesterol than sedentary men on average. Now that we've completed that hypothesis testing problem, let's take a look at a confidence interval problem. The setup is the same as before. We're looking at a sample of active men and a sample of sedentary men. But instead of trying to test a hypothesis, we're trying to find a 95% confidence interval for mu1 minus mu2. The formula that we're going to use is given on the slide. You can see that we actually already know all the numbers that we need to plug into this. Of course, we know x1 bar, x2 bar, 1 over n1, and 1 over n2. The only two numbers that could give us trouble are the t and the s, but we actually calculated those on the previous slides. The t is just the cutoff value that we found in that table of 2.08, and we showed how to find the value of s using that kind of complicated formula. So once we compute everything, we get a confidence interval of 12.9 plus or minus 11.1, and as usual, we're going to take 12.9 minus 11.1 to get the left endpoint, which is 1.8. And we'll do 12.9 plus 11.1 to get the right endpoint, which is 24. This means that we're 95% confident that mu1 minus mu2 is between 1.8 and 24. In other words, we're 95% confident that the difference in high-density cholesterol for active men and sedentary men is somewhere between 1.8 and 24. Now that we've conducted a hypothesis test and constructed a confidence interval using the same set of data, we might wonder if the answers to these two problems are consistent. So if we look at the hypothesis test that we performed, we rejected the hypothesis that mu1 is equal to mu2. In other words, we're saying it's very unlikely that mu1 is equal to mu2. But for simplicity, let's just go ahead and assume that mu1 is not equal to mu2. Well, if mu1's not equal to mu2, then mu1 minus mu2 is not 0. That's one conclusion that we can draw from that. Now let's look at the confidence interval. We have a confidence interval for mu1 minus mu2 that goes from 1.8 to 24. This also says that mu1 minus mu2 can't be 0. I mean, if mu1 minus mu2 is between 1.8 and 24, then it can't be 0. So the hypothesis test and the confidence interval are both saying it's very unlikely that mu1 minus mu2 is equal to 0, which is equivalent to saying it's very unlikely that mu1 is equal to mu2. So yes, the answers to these two questions are consistent. This is not a coincidence. This is actually always going to happen if you're doing a two-sample hypothesis test for population means, because really the same mathematical machinery is taking place in the hypothesis test and the confidence interval. So for population means, you'll always get a consistent result between a hypothesis test and a confidence interval. Now later on, when we start talking about population proportions, you do not necessarily get a consistent result because there are slightly different mathematical procedures used for the hypothesis test and the confidence interval. But even then, for population proportions, it will still almost always be consistent. It's going to be very rare, and you would have to have a particularly weird situation before you would actually get an inconsistent result. We were just discussing that the mathematics behind the hypothesis test and the confidence interval for a two-sample population mean problem are the same, and I'd like to look at that idea in a little more detail, mainly just because it can help you to keep your formulas straight. After you understand this idea, you can take the hypothesis test formula and use it to construct the confidence interval formula and vice versa. Now, I wouldn't actually recommend relying on that in order to figure out which formula to use. I would recommend that you write down a formula sheet that has every single statistical scenario that you might encounter and has the formulas for hypothesis testing and confidence interval clearly written out in each case. But this can still just kind of help you stay organized and just keep all of this stuff straight. Now, unfortunately, this will only work for two-sample hypothesis tests that involve population means. So it really only works for the first part of this lecture. So it doesn't really apply to the topics that we discussed in previous lectures. It could be modified to apply to that. And it also doesn't apply to the population proportion problems because, as we see, you use a slightly different procedure for the hypothesis test and for the confidence interval. But if you're looking at a two-sample problem that involves population means, then this method can really help you out a lot. So if we look at the confidence interval formula, we can make a lot better sense of this if we just think about the fact that we were trying to find a confidence interval for mu1 minus mu2. The thing in blue is called the estimator. So just think about that. If you wanted to estimate mu1, what would you use? You would use x1 bar. If you wanted to estimate mu2, what would you use? x2 bar. So if you wanted to estimate mu1 minus mu2, then you would use x1 bar minus x2 bar. So x1 bar minus x2 bar is just your estimator for mu1 minus mu2. But that's just a point estimator. That doesn't actually give us an interval. In order to get an interval, we have to look at the thing on the right. Now the thing on the right as a whole is the margin of error. The margin of error has two pieces. It has the statistical constant t sub alpha over 2, which is just the number that we look up in the table. And then it has a thing in red. And the thing in red is the standard error. Now, this formula is kind of complicated. But what's nice is once you understand this formula, you can see if we look up at the hypothesis testing formula, it's basically just this thing that's been rearranged. We have the estimator in the top now, and we have the standard error in the bottom. So this is a method that we can use to go from confidence interval to hypothesis testing. And similarly, you can see how we can go from a hypothesis test to a confidence interval by just kind of rearranging this formula in this manner. Now again, if you go back to the chapters before this, for whenever our hypothesis test was x bar minus mu naught over s over the square root of n, it'll be a little bit different because there's a minus mu naught in there. So you'll have to take that into account. So this won't work exactly, but I would encourage you to look back at those and just kind of see the connections there to kind of solidify your understanding of those topics. And I'll just repeat one more time. For the population proportion problems in the previous chapters and in this chapter, this just won't really work because you're using a slightly different procedure for the hypothesis test than you're using for the confidence interval. So far, we've performed a hypothesis test and constructed a confidence interval for one particular situation. And if you look back at the assumptions we were making in that problem, we were assuming that we had two statistically independent samples that had the same variance. So now let's go ahead and look at the idea of paired samples. So I just want to talk about what the difference is between having independent samples and having paired samples. So you get independent samples when you're just taking a sample from one group and then taking a completely different sample from a completely different group. So we looked at the case of active people versus sedentary people. That's just two different groups of people. So you're taking one sample from one group, one sample from the other group. They're completely statistically independent. Then if another example might be if you looked at a sample of people from New York and a sample of people from California, just two groups of people, they're going to be statistically independent. Or maybe you're looking at men and women. That would be the same thing. Now, an interesting example of independent samples that comes up in statistical studies is the idea of a control group and a treatment group. So that's when you are interested in, say, testing a drug. And so you take a group of volunteers, you randomly divide them into a treatment group and a control group. You give the treatment group the medicine and you give the control group a placebo, and then you look at the results of that in order to determine if the drug is working or not. Now, it turns out that actually in this case, those are not actually statistically independent, but you'll often see people saying that they're statistically independent because they can basically be treated as if they're statistically independent. So we have a little bit of math that tells us that we can do that. Now let's go ahead and look at some examples of paired samples. You have paired samples if there's a natural pairing between the elements in one sample and the members of the other sample. For example, let's say you just had a whole bunch of people and you measured the length of their left foot and the length of their right foot. Well, then all of the numbers that you get for the left feet would be one sample, and all the numbers that you get for the right feet would be another sample. But these aren't just two independent samples. There's a natural pairing between them. Namely, the left foot of a certain person is naturally paired with the right foot of that same person. So, Alice's left foot is going to be paired with Alice's right foot. Bob's left foot is going to be paired with Bob's right foot, and so on and so forth. You could say the same thing about math SAT and verbal SAT. If you had a bunch of students and you knew all of their math SAT scores and verbal SAT scores, well, those scores aren't statistically independent because someone with a higher math SAT score is actually likely to also have a higher verbal SAT score and vice versa. So it would be Alice's math SAT score is paired with Alice's verbal SAT score. Another interesting example is we said earlier that if you just took a random sample of men and a random sample of women, those would be statistically independent. One way that you might think that you could do that is just take a bunch of married couples and just take a random sample of married couples and then let the husbands be one sample and the wives be another sample. Well, those would not be statistically independent because there's a natural pairing. So each man is naturally paired with his wife, vice versa, right? So if you actually wanted a statistically independent sample of men and women, you would need to take a sample of men and then just completely separately and independent from those men, take another sample of women. One last example that's interesting from a clinical trials point of view is the idea of pre-op and post-op measures. For example, let's say we're going to perform a certain type of surgery on a patient. Then we can measure that patient's condition before they have the surgery, and then we can measure that patient's condition after they have the surgery. So we get two sets of numbers. We get all the numbers for all the patients before they have the surgery, and then we get all the numbers for all the patients after they have the surgery. And so we have two samples, but those are paired because each patient's pre-op number is naturally paired with that particular patient's post-op number. So this is an example of a hypothesis test that involves the pre-op and post-op values that we were just discussing. In this problem, we have 6 patients that started off with high systolic blood pressure. So you can see each patient's systolic blood pressure is listed in the column called pre-op systolic, and it's also labeled as X1. So then presumably we either perform a surgery on these patients or give them some kind of medication, and maybe we wait 6 months or a year, and then we measure their blood pressure later, and that's the post-op systolic value, which is labeled X2. And the question is the mean pre-op systolic blood pressure equal to the mean post-op systolic blood pressure? In other words, is mu1 equal to mu2, or are they different? We would hope that they're different, which would indicate that the procedure that we used is working. So the problem says, based on the table below, test the following at the alpha equals 0.05 significance level. Mu1 equals mu2 versus mu1's not equal to mu2. Okay, so this is a 2-sample hypothesis test that involves sample means. And so we're going to need to do a 2-sample t-test for means. As before, we need to think about what kind of assumptions are in place here. Are we dealing with 2 independent samples or 2 paired samples? Well, as discussed before, this is an example of paired samples. All these pre-op numbers are naturally paired with the post-op numbers. So these are paired. And when you're dealing with paired samples, you don't have to worry about whether the variances are equal or not. You just don't have to worry about that. but you do still need the populations to be normally distributed in order to perform these tests. And that's something that you'll either be told in the problem, or you could perform a statistical test to determine that. All right, let's solve this hypothesis testing problem. The first step in a paired samples problem is to create a third column, which is just the difference between the first two columns. You can see that the third column is labeled difference, and we say that d is equal to x2 minus x1. For example, 130 minus 190 is negative 60, 130 minus 210 is negative 80, and so on and so forth. The test statistic that we're going to use is given in the formula to the left. Now, I can say a little bit about where this formula comes from. By taking the difference between the first two columns, we've basically converted a two-sample problem into a one-sample problem. And we're just using the techniques from the previous chapters in order to perform the hypothesis test at this point. Now, the null hypothesis says that mu1 is equal to mu2. Well, that's the same thing as saying mu2 minus mu1 is 0. In other words, the null hypothesis is equivalent to saying that the mean for the random variable d is equal to 0. If you look back at the formulas we used before for hypothesis testing, it was x bar minus mu naught divided by s over the square root of n. So in this problem, we have d bar minus mu naught. Well, again, the mu naught is equal to 0. So we just have d bar divided by s sub d divided by the square root of n. So that explains a little bit about where the formula comes from. If you don't want to worry about that, you don't have to worry about that. The point is, in order to do the problem, we need to take the difference between the first two columns and get a third column d, and then we need to use the formula on the left in order to calculate the test statistic. Now, there are two numbers in this formula that we don't know. They weren't given to us in the problem, d bar and s sub d. So we're going to have to calculate those ourselves. D bar is just the average of the d values, so we just add all of those up and divide by 6, and when we do that we get negative 70. And SD squared is the sample variance of the d column. So we did discuss that in chapter 2 in the second lecture. So remember how we do that. We're going to take each number in that column and subtract the mean, which is negative 70. We're going to square that result. We're going to do that for each of these numbers and add all those results together. And then we divide that answer by 1 over n minus 1, which in this case is 1 over 6 minus 1. Whenever you do that, you'll get 80. And then the square root of 80 is equal to 8.94, and so s sub d is equal to 8.94. So plugging the two numbers we got here into the formula and plugging our sample size in, which is 6, we calculate our value for our t statistic, which is negative 19.18. And as always, the hypothesis test has two steps. We need to calculate our test statistic, and then we need to compare it to a cutoff value in order to figure out whether we're going to reject or retain the null hypothesis. So we're done with the first step. Let's go ahead and do the second step now. Let's figure out what our cutoff value is going to be. Since we have a small sample size, we're going to use a t-distribution to get our cutoff, which means we need to figure out how many degrees of freedom we have. In a paired sample problem, you're basically converting it to a one-sample problem, so your degrees of freedom is just n minus 1. In this case, that's 6 minus 1, which is 5. So we just need to find the cutoff value for a t-distribution with 5 degrees of freedom, using an alpha of 0.05, and that's 2.571. And finally, we compare our test statistic to the cutoff value. Here our cutoff value is 2.571, and our test statistic was negative 19.18, which is way to the left in the rejection region. So we are going to reject the null hypothesis here. Let's think a little bit about what that means from a conceptual point of view. We were testing the hypothesis that mu1 is equal to mu2. That means the pre-op systolic blood pressure is equal to the post-op systolic blood pressure on average. Well, we're rejecting that claim, which means that this analysis provides pretty strong evidence that the treatment we gave these patients did lower their systolic blood pressure. The only problem I would have with this study is there's no control group, so we don't know if this decrease is actually due to the treatment or if it's due to some other factor like the placebo effect. So really, to improve this study, you would take a group of volunteers, break them into two groups, have a treatment group, which is basically what we're looking at here, but then you would also have a control group where you give them a placebo, And then you could take the differences for the treatment group and compare those to the differences for the control group, and that would use a two-sample independent test. And then that would help you to make a little bit stronger conclusions here. Now we've done two examples that involve two-sample population mean problems, so we're going to turn our attention to population proportion problems. Remember that population proportions are when you're dealing with dichotomous data, so basically yes-no binary type data. So let's go ahead and take a look at this problem. We have two medicines, and the first one cured 63 out of the 91 patients that it was tested on. The second one cured 53 out of 79 patients that it was tested on. It says test the following at the alpha equals 0.01 significance level. P1 equals P2 versus P1 not equal to P2. In order to do this, we're going to use a two-sample z-test for proportions. The only assumption that we need to make here is that the samples are statistically independent. As always, the hypothesis test involves two steps, calculating a test statistic and then comparing it to a cutoff value. The z-statistic that we're going to use is given by the formula on the left. And let's remind ourselves what the p-hats in this formula represent. So keep in mind that P1 basically represents the proportion of people that were cured by the first medicine. P2 represents the proportion of people that were cured by the second medicine. So in order to estimate those, we're just going to do the common sense thing. If the first medicine cured 63 out of 91 people, then we're going to do 63 divided by 91 and we get 0.692. You can sort of think of that as 69% of the patients were cured by the first medicine. Similarly, we get about 67% of the patients were cured by the second medicine. So that's our P1 hat and our P2 hat. We also need to calculate a P hat. And this is sort of like our S from earlier. It uses both data sets to calculate it. What this P hat represents is how many patients, what percentage of patients overall were cured by both medicines combined. So the total number of people that were cured is 63 plus 53, and the total number of patients in the study is 91 plus 79. So if we look at that ratio, we get about 68% of the patients in this study were cured. Now we can just take the numbers that we calculated and plug those into the formula. Notice that our N1 is equal to 91 since we have a sample of size 91 for our first group. We have a sample of size 79 for our second group, so our N2 is equal to 79. Let's just plug all those numbers in. We get a z of negative 0.293. Then we, of course, need to compare that to the cutoff value. What type of cutoff value are we going to use? Well, we're doing a z-test here, so we're going to use a standard normal cutoff value. We have an alpha level of 0.01, and so if you look up the cutoff value for a standard normal distribution with an alpha of 0.01, that's 2.58. Our z-statistic is negative 0.293, which is well within the center region, and so we're going to retain the null hypothesis H0 here. What that means from a practical standpoint is we don't really have strong enough evidence to conclude that these medicines are different. As far as we can tell, it looks like they're pretty much the same with respect to their ability to cure patients. Now that we've performed that hypothesis test, let's go ahead and construct a 99% confidence interval for P2 minus P1. The formula that we're going to use is just given on this slide. And we've already seen how to calculate all the numbers that we need in this formula in the previous hypothesis testing problem. Notice here that we just need to calculate P1 hat and P2 hat. We don't actually have the P hat that uses both samples in this situation. And that actually goes to show why the confidence interval formula is using a little bit different approach from the hypothesis testing formula. In any case, we just calculate these numbers and plug them in. Once we perform these computations, we get a confidence interval of negative 0.021 plus or minus 0.185. As before, we take the first number and subtract the second number to get negative 0.206, and then we add these two numbers and we get 0.164. So we're 99% confident that the difference between P2 and P1 is somewhere between negative 0.206 and 0.164. Once again, we've taken the same data set and used it to perform a hypothesis test and to calculate a confidence interval. So we can ask the question, are our answers consistent? When we did the hypothesis test, we retained the hypothesis that P1 is equal to P2. It doesn't mean that we know P1 is equal to P2. What we're saying is we don't have enough evidence to reject that, and so in other words, P1 could be P2. Well, if P1 could be P2, then P2 minus P1 could be 0. That's what we can conclude from the hypothesis test. Let's look at the confidence interval. The confidence interval for P2 minus P1 is anything between negative 0.206 and 0.164. Notice this shows us that P2 minus P1 could be negative or it could be positive. So we don't actually know which medicine is better. If P2 minus P1 is positive, then the second medicine is better. If P2 minus P1 is negative, then the first medicine is better. And also P2 minus P1 could be 0, which would indicate that the medicines are equal. So we actually don't know if either one of these medicines is better than the other one. And for all we know, they're equal, which means that our statistical test just wasn't conclusive in answering the question of which one of these medicines is better. But to get more to the point on what this question is asking, if P2 minus P1 can be anything between negative 0.206 and 0.164, well then in particular it could be 0. So the hypothesis test is saying that P2 minus P1 could be 0, and the confidence interval is saying that P2 minus P1 could be 0. In other words, the answers to these questions are consistent. As stated earlier in the lecture, it is possible that you could get an inconsistent result for this type of problem, but it's really not very likely. Because the procedures are different, you could get a different result, but again, it would have to be a pretty strange situation where the P2 hat and the P1 hat are very different in order for something like that to happen. Well, that wraps up this supplemental lecture, and as always, please let me know if you guys have any questions and I'll be happy to help you out. Let me know if there's anything I can do to improve these, or let me know if there's something you liked or if something you didn't like. But until next time, I'll see you later.